All right, folks, we're here today to talk about 4.3, the natural exponential function. And this is a follow-up to section 4.2, which talked about exponential functions in general. Now, if you recall from 4.2, a regular exponential function we said was y equals a to the x. And it was important that the variable was in the exponent. That's what makes it an exponential function. Today we're going to talk about the natural exponential function. All right, so the natural exponential function. Now, the definition of the natural exponential function is as follows. It is a function defined by f of x equals e to the x. And this is going to be true for every real number x. And you might also see that written as x is an element of the real numbers. Okay, same thing. Now, what is this e? Because I've used this in the 4.2 video, so you might be wondering, what is this e? Well, the number e is this. If n is a positive integer, all right, so n has to be a number like 1, 2, 3, etc., etc. And we use this formula, 1 plus 1 over n to the power of n. As this expression gets close to infinity, meaning I put a really big number in for n, then the value is going to approximate 2.71828, and that is our number e. All right, so let's talk about finding zeros of some exponential equations. So in 4.2 we talked about having being able to solve exponential equations, and here we're trying to find out where the zeros are, or another way of saying find the zeros is find the x-intercepts, all right? Now, before we take a look at these examples, since we're looking for x-intercepts, I just want to remind you that you could go to Desmos to graph any of these functions afterwards and check your answers to see that we've got all of the zeros or all of the x-intercepts, okay? All right, so let's go ahead and get started with this question. So, f of x equals negative 2x squared e to the negative 2x plus 2x e to the negative 2x. Now, I know that looks like a pretty complicated looking situation, but what we're going to go ahead and do is we're just going to set that whole function equal to 0. And we're going to go through and see if we can find any common factors between the first term and the second term. And so I notice that the first term has a 2, and so does the second term. And I also notice that this one has an e to the 2x, and so does this one. And then I notice that this one has an x and this one has an x squared. So when I factor out my greatest common factor, there's still going to be an x left in this spot. All right, so my greatest common factor, I saw 2 in both of them, I saw an x in both of them, and I saw e to the negative 2x in both of them. That is my greatest common factor. Now, what's left? I've got a negative sign. Don't forget about that negative sign. Negative x plus, now since I took everything out of here, it doesn't go to 0, but it actually goes to 1. Now, let's take a look at what parts can actually equal 0. So if you recall from the last section, 4.2, exponential functions like e to the negative 2x, they actually never cross the x-axis. All right, so let me write that off to the side. This one has no x-intercept. What that means is the other parts of the function are going to be responsible for the x-intercepts. So I've got this front part here, 2x, and 2x can equal 0 when x equals 0. So this, if you graph it on Desmos, should be one of the x-intercepts. The other 0, or x-intercept, comes from this last part, negative x plus 1. So if I take negative x plus 1 and I set it equal to 0, I'm going to go ahead and add x to both sides, so I get x equals 1. That is going to be our second x-intercept, okay? So our goal here is to find our greatest common factor, all right? We're going to find that greatest common factor. We're going to see which parts have no x-intercepts, and then find the x-intercepts from the parts that actually impact it. Okay, let's move on to example number 2. Example number 2 says f of x equals x e to the x. And we're going to start the same way, where we set it equal to 0, because that's what we're doing when we find x-intercepts. And like last time, we're going to go ahead and see what are my greatest common factors. So I notice this one has an e to the x, and so does this one, and that's it. So I'm going to go ahead and pull an e to the x out to the front. The first term will still have the x, plus, even though this whole thing got taken away, we need a 1 there to keep its place. All right, this e to the x, like last time, has no x-intercept, which means that the only parts that help us find the x-intercept for this function is going to be when x plus 1 equals 0. And I'm going to subtract 1 from both sides, and I'll get x equals negative 1. So this function only has one x-intercept, while the other function we saw in example 1 has 2. All right, let's take a look at one last example here. This one is pretty long and messy, but whenever I look at these functions, I do like to see if there are any like terms that I can combine right off the bat, okay? And I look and I notice that this first term has x squared e to the x, but this last term has 3 x squared e to the x. So I can actually combine those together. And I'm going to take the moment to rewrite my equation. So I'll have 0 equals, instead of x squared e to the x, I'm going to have 4 of them. 1 from the front, 3 from the back. Plus 2x e to the x plus x cubed e to the x. Okay, time to look for that greatest common factor. So I notice there's an e to the x in all of them. I notice that each of them, this one has 1. I can take 1 from here. I can take 1 from here. And that looks about it. So I took out an x, I took out e to the x, and everything else stays in there. So the first term has 4x, plus the second term has 2, plus the third term has x squared. Okay, let's see if we can see what does not contribute to our x-intercepts. There it is, that exponential does not contribute to the x-intercept. So I just have x equals 0 as one of my x-intercepts. And then the other one, if I write it in a more familiar form, x squared plus 4x plus 2, that might help me determine whether or not I am able to factor that quadratic. So if we were to graph that function, okay, so you're always welcome to graph it on Desmos. If you were to graph that function, just this part, you would get a parabola that kind of looks like this, okay? That means that this function, or this part of the function, actually contributes not 1, but 2 x-intercepts. Now, because this one is not factorable, we're going to have to use our good old friend, the quadratic formula. Okay, I get -4 plus or minus 16 minus 4 times 2 times 1 is 8 over 2 times 1 is 2. That gives me -4 plus or minus the square root of 8 over 2. Now, if you turn both of those into decimals, okay, let's see what we're going to get. We get -4 minus square root of 8, and then we divide it by 2. We should get -3.414. And if we do -4 plus square root of 8, and then we divide by 2, we should get -0.586. So this long question has 1, 2, 3 x-intercepts, or 3 x-intercepts, or sometimes we call them zeros. Okay? All right, let's move on to the second part of this section, which is applications. Now, there's one formula that we're going to use for both of these applications, and that is A equals P e to the RT. And yes, that little e is exactly the e that we talked about from earlier, and e is around 2.718, okay? But let's talk about what some of these other letters mean. So T is going to stand for time. And a lot of times we use this equation with money things. So we'll be talking about maybe how long you want to save your money for, how long you want to take a loan out for, and that's going to be the time. This R, okay, that is your interest rate. We want to make sure, though, when we put this into our equation, that we use a decimal and not just the percent. Okay, this E we talked about earlier, E is about 2.718. The principal is what this P stands for. Principal meaning your starting amount of money, not like principal and vice principal of a school, okay? So this is your initial amount of money. And last but not least, our A stands for our end amount of money. So A equals PE to the RT. Let's take a look at two examples. All right. So the average rate of return on something called an IRA, or an individual retirement account, is 6% per year. Now, I think right now with our pandemic going on, 6% is definitely not real, but on the average, every year you can expect that your retirement account will earn about 6%, okay? So if you invest $6,000 this year in an IRA, find the value of your investment after 30 years. Now, some of you might be saying, who's got $6,000 to put away? Why did she pick such a big number? Well, this $6,000 is actually the most that you can put into your IRA every year. And that number changes as you get older, and sometimes the government changes the number if they want people to be saving more, but right now it's $6,000 a year. And that's your own money that you're putting away into your own account. The reason why I chose the 30 years is I want us to imagine a scenario where you're listening to this lecture and you're like, all right, Judy told me to go ahead and put $6,000 away, so I'm going to put $6,000 away. And then you forget about it until you retire, which maybe is 30 years from now, maybe more. But let's say you forget about it for 30 years. You don't do anything with that. I want to see what happens to that money if you put it away now and you don't do anything with it for 30 years. Okay? So, we're going to use our equation, A equals PE to the RT. We want 6,000 to be our principal because that's our initial investment. E, our R is not going to be 6, but it's going to be 0.06. And then our time is going to be 30. Now, if you watch the 4.2 video, I made a big deal about how we have to find this number first because we want to make sure that we follow our order of operations. And when we do that, we'll get 6,000 times, let's make sure we have the right decimal here, 6.049647464. Write out as many as you can because the earlier you round, the more off your answer is likely to be. And when we multiply that out, it turns out that you put away $6,000 now and you forget about it, in 30 years, you're going to have, that's right, that's a comma, $36,297.86. Now, I know $6,000 is a lot. It's a lot for you, it's a lot for me, but the beauty in putting away this money, you made an extra $30,000. You turned $6,000 into $30,000, and you didn't do anything but put it away into an investment account for 30 years. So imagine if you put $60,000 or $6,000 in every single year, how big that number could get. Okay? All right, last example that we're going to finish off with here is maybe the flip side of investment accounts, which is credit cards or debt. Now, I know debt is a big thing for a lot of us, and sometimes it feels like it's spiraling out of control. But I also wanted us to be aware of like how credit card companies make their money. So it says here that the average APR, or annual percentage rate, for a credit card is 21%. If you spend $500 in 1 month and do not pay your bill, how much will you owe in 1 month? And then how much will you owe if you just kind of hope it goes away for 6 months? So we're going to use our same formula, A equals PE to the RT. And we're going to solve this once with T equals 1 month and once as T equals 6 months. See what that difference is. Okay, so 1 month and 6 months. We're going to start with our 500 E to the, don't put a 21 here, but put a 0.21, and then times 1 for the 1 month. And on the other side, we'll do 500 E to the 0.21 times 6. Do this part first. Do this part first. When you multiply all of this out, you should get $616.84. That means if you weren't able to pay a $500 bill in 1 month, then the next month they're going to charge you an extra $116.84, even if you didn't spend any more money. Let's see what happens if we do this for 6 months. I got a comma in this number. That's not good. You don't pay that credit card bill for 6 months, you're going to owe a lot of money, way more than whatever you spent to buy your $500 stuff. Okay? Now, I know sometimes things can't be helped, like insurance bills come up or whatever it might be, but if you can try and avoid not being able to pay that bill, it definitely is something that'll be beneficial for you. Okay? So, a little bit of math, a little bit of money sense from Judy. Do with it what you will. But that's it for 4.3. Thanks so much, folks.